Okay, we were talking last time about section 1.9, the matrix of a linear transformation. And what we're doing is we are uh, constructing matrices that transform points in the xy plane to new points in the xy plane. And there are all kinds of things we can do, all kinds of transformations that we can do. We can reflect points about the x1 axis, which is like the x-axis. We can reflect points about the x2 axis, which is the y-axis. We can also rotate points a certain number of degrees. And in this problem here, and I'll get to that one question, in this problem here, what we want to do is we want to rotate points -3⁴ radians clockwise. So that's -135 degrees clockwise. And then we want to reflect the points through the horizontal x1 axis. So there is some standard matrix, a 2x2 standard matrix with 4 entries that will do that. And we have to figure out what that standard matrix is. And you learned back in section 1.8, section 1.8 was, well, actually, no. Section 1.8, you were introduced to transformations, the definition of a linear transformation. Somebody asked about the shearing of the sheep, the shear transformation. That was in sample 3 from section 1.8. But in section 1.9, we had a theorem that said if you want to find the standard matrix that'll do the job, that'll do the transformation you want, the columns of the standard matrix would just consist of the transformation of the unit vector E1, which is like the I vector, and the transformation of unit vector E2. E2 is the J vector. So this comes from theorem 10 in section 1.9. So what makes this different than the previous problem we did? We looked at some different types of standard matrices for different types of transformations. There's a table 1 and a table 2 at the end of section 1.9 that has a goldfish, and the goldfish is being reflected about different axes. It's being shrunken, it's being expanded, and then there's shear transformations too, and they provide all the standard matrices that do that job. And we showed through section 9 theorem 10 how those matrices are derived. But in this problem, what makes it a little different, again, is that you're not really doing just one transformation, you're doing two. You're doing a composition of two transformations. You have a rotation of rotating points -135 degrees clockwise, and then you have a reflection of the points through the horizontal x1 axis. So what would the standard matrix of the transformation that maps coordinates in the xy plane, which is r squared, or I should say x1, x2 plane, what would the transformation that maps coordinates in the x1, x2 plane to new coordinates in the x1, x2 plane look like? Well, let me show you. Okay, so, well, yeah, and I'll tell you what, let me give you a moment to think about it, and then I'll show you the answer here, okay? I'll give you a moment to think about it. All right, well, let me show you how we would work it. it's really not all that different from the previous example that we looked at. Take a look here. So the goal, of course, is to find out what the vectors are under the transformation. So the transformation of E1, transformation of E2. So what we do, what I do, this is how I do it. E1 is 1, 0. So that's this point right here. Now, what do we want to do with that point? We want to rotate that point clockwise 135 degrees. And if we did that, the point 1, 0 would become the point negative root 2, negative root 2, right? Because the vector itself, here has length 1, right? So this vector here also has length 1. That's why you have negative root 2, negative root 2 over 2, and negative root 2 over 2. How many recall these kind of values from the unit circle? How many recall those kind of values from based off of a unit circle in trigonometry? Sure, Mikhail recalls that. But what do we do now? Now that we've done the rotation of the point 135 degrees counterclockwise, now what we have to do with the point is reflect the point about the x1 axis. So the negative 2, this point here, let me make it nice, and this point here now, when we reflect it about the x1 axis, you're going to end up at this point. And that point has coordinates negative root 2 over 2 and positive root 2 over 2. The x coordinate didn't change, but the y coordinate did. And so that's how you generate your T of E1 vector. Let me give you a moment to copy that and see. Let's see if there are any questions, okay? Let's see if there are any questions. Okay, all right, Mikhail, very good. Okay. All right, well, okay, no problem. Well, let's take a look at now the point 0, 1, which is the E2 vector. So the E2 vector is the point 0, 1, and we are rotating that 135 degrees clockwise. So there it is. There's that rotation. And then here's the vector. And that vector has coordinates root 2 over 2 and negative root 2 over 2. But then what are we doing? What are we doing with that point? Well, we're reflecting it about the x1 axis. And when we do that, that gets us up here to positive root 2 over 2, positive root 2 over 2. And that then is the transformed E2 unit vector. Okay, so that's how you handle those kind of situations where you have multiple transformations in conjunction with each other. And so by theorem 10 from section 1.9, right, the matrix A for our transformation is the matrix you see there, where the column vectors consist of, first column vector of the matrix A is T of E1, that transform vector. The second column vector is transform vector E2, transform of E2. It's that simple. It's that simple, really. And it kind of makes sense. It kind of makes sense because the 2 by 2 matrix acts on coordinates, x1, x2 coordinates. So you're just locking in the really what you're using 2 points to help you lock in what the matrix has to be. And the 2 points or vectors that you're using are those 2 unit vectors, and then studying the transformations. If it's true for them, it would be true for any other points that you could use. Quite fascinating, really. Yes, Mikhail, this does extend into n-dimensional space. One moment, let me bring up the ebook. Okay, I have the ebook here. Let me bring it up and show you that theorem 10, the all-important theorem 10 here. Let's see here. So boom, boom. We go into application. Wait, no. This is what I want. Yeah, there's the theorem 10. And you see the transformation takes you from n-dimensional space to m-dimensional space. Okay, it's a very general theorem. Now, in our case, we went from 2-dimensional space to 2-dimensional space, but here we're going from n-dimensional space to m-dimensional space. And so I want to say this the right way. So the matrix A in this case, the matrix A would be an m by n matrix. Hold on here. Matrix A would be an m by n matrix. And so the column vectors in that matrix A below, the transformation vectors, would, what would how many rows would they have? How many rows would they have to have? So if A is an m by n matrix, what tells you the number of rows, the m or the n? The m. That's right, Mikhail. So that's right, Jacob. So those vectors are have m entries in them. So this is applicable to you know, a lot of different situations. Let me see. There's a comment here. 3D graphics for a computer screen. Let me think on that. One moment. One moment. So 3D graphics for a computer screen. Hold on. I don't think so quickly. Yeah. N would be 3 and M would be 2, because if let me just go to the whiteboard here and show you that. That was a good comment there. Yeah, Mikhail brought that comment there. So let me show you why that is. So if you're okay, so and I have to be a little careful on this, but let's say, like, television. You have people in three-dimensional space doing things. Okay, three-dimensional space doing things, but then you watch them on the television. Okay, well, on television, the two-dimensional screen, coordinates, x1, x2, x3 coordinates get transferred into two-dimensional coordinates. Okay, now I'm sure there's a little more, you know what I mean, involved in that, but let's just keep it simple. So let's say the two-dimensional coordinates, the new ones, are y1, y2. Well, you need a matrix. That's going to take three-dimensional coordinates, okay, that's a 3 by 1 there, and convert them into 2 by 1 coordinates. So what you would need here is a 2 by 3 matrix, because a 2 by 3 matrix times a 3 by 1 matrix will, since the column number of the first matrix matches the row number of the second matrix, so the resulting matrix, which would be a vector, would be 2 by 1. And so you'd have to have 3 columns, and those 3 columns would be determined by whatever the transformations of the unit vectors E1, E2, and E3 are, or I, J, and K. Okay, you see that? Yeah, pretty cool. Pretty cool. I agree. It really is. It really is. And I encourage everybody. I teach calculus too, and I have students who are they're also computer science majors, and I'm encouraging them to take linear algebra because I think it'll just help them. They'll see a lot of nice applications. Well, let's do another example here. I want to do another example before we go on break here. So let me bring that example up. Let me see. Hopefully I have it here. Yeah, this is one. Okay, so this is a little more theoretical, this example, but you're going to have a good understanding of it when we're done. By the way, how many remember with functions, one-to-one functions, one-to-one, and onto mappings with functions? Does anybody recall that in school, like high school, or Mikhail does? One-to-one functions. Okay, all right, very good. Onto. All right. Well, let me give you a chance to copy this example down, and then we will proceed on to the solution. Okay, so let's first of all just refresh our memories on what a one-to-one function is. So let me go into the whiteboard here and clear that. So one-to-one function. So if you had f of x equal to 2 times x, is that one-to-one? We use that as an abbreviation. Is that one-to-one, that function? It is, absolutely. If, for instance, if x equals 1, f of 1 is 2 times 1, and that equals 2. And so x equals 1 is associated with the function value of 2, and there's no other x value that will give you that function value. Okay, if x is 3, f of 3 is 2 times 3, and that's 6. So no other function value would give you that. So like x1 goes to y1, x2 goes to y2, and if x1 is not equal to x2, this implies that y1 is not equal to y2. Okay, so that's an example of a one-to-one function. Okay, does this help? Does this help kind of jar your memory a little bit? It always helps to have an example. Good. All right. Thank you, Marcella. And by the way, not one-to-one would be something like f of x equals x squared. Because there, if x equals 1, this means that y equals 1. Y would be 1 squared, which is 1. And if x equals negative 1, this implies that y would be negative 1 squared, which is also 1. So you see, you were able to get a y value of 1 using 2 different x values. So that's not a one-to-one function. The same kind of thinking can be applied for this kind of problem. Okay, and you have to think very, it always helps to think of an example like this. And now we go back to our example here that we're doing. So, okay, so in this case, we have a transformation. We have a transformation that is now. Let me ask you this. Well, yeah. So the transformation is taking coordinates in R2, vectors in R2, and mapping them into vectors in R what? In R. So the transformation is taking vectors in R2, good, Jacob, and mapping them into vectors in R3. Okay, so, and we want to know if a vector, if you have different vectors in R2, would they map to different vectors into R3? Well, we're not doing on2 yet. We're just doing one-to-one. We're just doing one-to-one. We'll get into the on2 part next. This function, yeah, it turns out that it is one-to-one, and I'll show you why. Let's go to a solution of this. So it helps to come up with the standard matrix A. So what I did was I wrote out you have the transformation of the vector consists of 3 coordinates. And I wrote the 3 coordinates in as just a vector. So vectors can be represented by points. You know, the 3 coordinates, they can be written as, you know, this column vector. That's fine. And it's not too hard to see that the standard matrix for this linear transformation, and I'm calling it a linear transformation because we learned that when you have a transformation defined by A times X, that meets the definition, or that meets the requirements of a linear transformation. We looked at that back in section 1.8 when we looked at the definition of a linear transformation. So I mean, they gave me enough information so I could figure out the standard matrix of the linear transformation. Okay, I didn't have to do any like pictures or diagrams or anything like that, like the previous problem. Well, what we can do, you see, is we have A times X here, right? We have A times X, but we could write that as a linear combination of the column vectors of the matrix A. Column vectors being A1, which is 3, 5, 1, and vector A2, which is 1, 7, 3. So pictorially, this is what you're doing here. Pictorially, this is what you're doing. You're taking a vector in the R squared, which is the, you know, the X1, X2 plane, and you're mapping it to a vector Y in 3-dimensional space. But keep in mind, the column vectors A1 and A2, these are linearly independent, form a linearly independent set. The column the vector A2 is not a multiple of the vector A1. So the set of vectors A1, A2 is a linearly independent set, okay? But just keep in mind, they don't span all of R3. The span of the vectors A1, A2 is a 2-dimensional space in R3, right? It couldn't be a 3-dimensional space. You would need 3 vectors, a span of 3 linearly independent vectors to get a 3-dimensional space. We just have the span of 2 linearly independent vectors that live in R3. And geometrically, that span would represent a plane, in R3. Okay, that's what it would be. Now, what I have up here, you notice, is I'm stating that this is the plane. So how am I coming up with that? Don't worry about that yet. Just put it in your notes. I'll show you how I justify that. But the key point here is that any vector x, any point x or vector x in R2 would have to map to a unique vector in R3, because we're taking a linear combination of 2 linearly independent vectors. So that ensures that that every x in R squared maps to a unique vector y in R cubed, because of the linearly independence of the vectors A1, A2, and therefore the transformation is 1-to-1. Okay, and this relates to a theorem 12 in your textbook, theorem 12. part B, which states the transformation is 1-to-1 if and only if the columns of the matrix A, the column vectors, are linearly independent. And sure, the theorem's there, but I wanted you to just sort of get an intuitive feel for this. If you were to change like change x1 and x2, change the weights on those vectors a1, a2, the coordinate with the coordinates, the point with those weights will be a different point, and it would map to a different vector y in three-dimensional space. Are you intuitively seeing this? That the transformation has to be 1-to-1? Okay, Mikhail's saying it. Very good. Let me give you an example. Well, let me give you an example of something where this one would not occur. Let me just give an analogy here. Let's say, let me go to the whiteboard. I'll come back to that. Let's say that you had x1 times 3 vector 3, 5, 1 plus x2 times the vector 6, 10, 2. Okay, just as an example. Are these vectors here, are they linearly independent or linearly dependent? Linearly dependent. That's absolutely right. Because the second vector is a multiple of the first vector, right? The second vector is what scalar times the first vector? 6, 10, 2 is what multiple of 3, 5, 1? Good. Good. So in this case, A2 is 2 times A1. Okay, thank you. Thank you. So look what happens here. Look what happens. Let's say that you have, so we'll call this, this is our y vector here. This is our y vector. And let's say you have x1 equals, let's say you have x1 equals 1 and x2 equals 1. What would that mean that the y vector is going to be? The y vector would be 1 times 3, 5, 1 plus 1 times 6, 10, 2. And what's that going to give you? What vector is that going to give you? It's a 3 by 1, and what are the coordinates of the vector? What are the entries? What's the first entry? Okay, good. 9, 15. That's right, Bella. 9, 15, and 2. Okay, now let's take then another combination. That's right. Let's say x1 were equal to 3 and x2 were equal to 0. Okay. What would the y vector be? Well, the y vector would be 3 times 3, 5, 1 plus 0 times 6, 10, 2. And what's that going to give you? Nine. Let me see here. I'd like to say, hold on. Oh, I think I have a little typo here. Here, I want a 3, right? I want a 3 there. Okay, same thing. So, all right, so what you're going to get is 9, 15, 3. So see, you got the y, you got the same y vector. Even though your x1, x2, your coordinates were different, you got the same y vector as when, so using coordinates 3, 0, you know, x1 equals 3, x2 equals 0, you got the vector, the y vector 9, 15, 3. Well, you also got the vector 9, 15, 3 when you use the coordinates x1 equals 1, x2 equals 1. So x2 1 equals 1, x2 equals 1. Well, what I'm trying to say graphically is you have two vectors here. Maybe I'll put it in black. Keep this separate. You have two vectors, an x1 and an x2. Okay. In this case, here's x1 and here's x2. You have two vectors that map to the same y vector, right? And that occurred because these column vectors, okay, well, these vectors were linearly dependent. So you see, that means you have not one-to-one, not one-to-one. Okay, was that helpful? Was that helpful? To sort of give you these, okay, wonderful, Bill, and excellent. These concepts can seem a little abstract, but if you just create little examples, you know, for yourself, then the concepts seem more clear, and that's what we want. That's what we want. Okay. Now let's go back to the example here. This is all in the recording. Okay, so now we're being asked, does the transformation map r squared onto R3? Okay. In other words, for every vector, I want to say this the right way, one moment, to make sure I'm saying it the right way. Yeah. What does this mean, R2, the transformation mapping R2 onto R3? I can tell you the answer is going to be no. Okay, but let's see why. So, okay, if the transformation here one moment. So if the transformation maps r squared onto R3, then every vector y in R3 would have to be the image of some vector r in R squared. In other words, every vector in that three-dimensional space R3 could be reached by taking the transformation of some vector in R squared. So let's see if that's true. Let's see if that's true. So this is a little bit like, I don't know if you've seen the movie I, Robot with Will Smith, where he has to track down who killed the professor. Does anybody, that movie's a little bit older, but I don't know if you've heard of that movie. But in the movie, he's trying to seek an answer, and the professor pops up every once in a while to help guide him. So here, we just have to ask the right question to be able to see that this function's not onto. And the question is this. This is the key question. Does the transformation, okay, which is equal to A times that 3x2 matrix A times a vector X, does that transformation have a solution for every vector Y in R cubed? Let's see. So I take the matrix equation. Here it is. I take the matrix equation and I write it as this augmented matrix. Okay, which we know how to do because we've studied section 1.4. And I'm going to try to solve the augmented matrix. Okay, so let's see here. I guess I can label some row operations. So here I took -3 times row 1, added it to row 2, put the result in row 2. Let me just hold on here. Clear that. I want to have just a little bit better here. So I took -3 times row 1, added it to row 2, and put the result in row 2. And then, I want a 0 here, and I want a 0 where the 5 is. So I have to take -5 times row 1, add that to row 3, and replace row 3 with that summation. Okay, and what I'm trying to do is I'm trying to get this augmented matrix here in echelon form. Okay. Now, here where the -8 is, I want a 0 there also, trying to get it in echelon form. So what I had to do, I guess I'll have to put what I did to the left. I'm using the -8 here as a pivot. Okay, to get the zeros in these spots, I use the 1 up here as a pivot, but now I'm going to use this -8 as a pivot to produce a 0 where that -8 is in the third row. So I'm just going to take -1 times row 1, add it to row 3, sorry. No, -1 times row 2, add that to row 3. Let's try to make this a little bit nicer. Okay, and gonna replace row 3 with that summation. And this is what you get. So look at the third row. On the right, the y2 minus 5y3 plus -1 times y1 minus 3y3, that can be simplified to -1 minus 2y3 plus y2. So the system, turns out, is consistent only for vectors y, okay, vectors y, y vectors, I should say, okay, whose coordinates satisfy that constraint. And that excludes many vectors y in R cubed. So T does not map R squared onto R cubed. It does not. And the picture on the previous page, remember I said that what does the range look like under this transformation? I said it was the plane. I said it was this plane here, negative y1 minus 2y3 plus y2 equals 0. And that's because the y coordinates have to satisfy that constraint. So that means, hey, that's your plane. That's going to be a plane. In order for the transformation to map onto R3, you need to have three vectors. The matrix A has to consist of three linearly independent vectors. And our matrix A, remember, which was our matrix A, if you remember, our matrix A, which was 3, 5, 1, 1, 7, 3. Our matrix A only had two linearly independent vectors. Okay, so because the column vectors of the matrix A do not span R3, you don't have an onto transformation here, and that's theorem 12 part A. That's theorem 12 part A, which I'll bring up here. But let me give you a moment to hold on here while you're doing that. Are there any questions that you have here? Okay, so let me go to the book then. If does anybody need more time to copy, or is everybody good here? Maybe give me a thumbs up if you're good. Okay, Mikhail's good. Marcella's good. All right. Belen's good. Yasin's good. Excellent. Okay. Let me just show that theorem. Theorem 12. See? So this example that we did is basically a concrete example that reinforces theorem 12 so that it doesn't seem so abstract. The way we understand theorems which appear abstract, which are, theorems are always in general, right? But the way, but how many find that to understand a theorem, to do a multiple choice problem, for instance, that might be theoretical or conceptual, how many find it helpful to look at a concrete example to then help you understand the theorem or the concepts? Okay, good, good. Michaela and Marcella agree, and that's what really you want to be doing. You know, those multiple choice exercises that you get in your homework. You know, you want to take your time in answering them, and sort of come up with examples that'll help you maybe disprove something. You know, a lot of times, how do you disprove a statement? You find a counterexample. You know, so. All right, well, great. Are there any questions before I stop the recording? Okay. Well, we are. I think we've covered section 1.9 pretty well now. All right, excellent.